Number 5, and this is our 13th problem. This is an extremely easy problem. This is a wording confusing problem. Sometimes I kind of glance ahead, especially if it's like super wordy. If I look down at my answer key or my answer choices really quick, it's trying to tell me that it's valid or not valid. So I'm probably looking at the what of this problem. What things would make the problem valid or invalid? Probably conditions. Now, you don't have to look ahead to know what you're dealing with, but sometimes I do that. All right, so the city's interested in building a waste management facility in a certain area. 100 randomly selected residents were asked for in random. You support the city's decision to build a waste management facility in their area. Of the 100 residents, 54 said no, 4 said yes, 42 had no opinion. We've got our confidence interval constructed from these data to estimate the portion of this area's residents who support building a waste management facility in their area. All right, this first one. Because a sample size of more than 30 was used. What is that statement just there talking about? And which? So this is checking normal by central limit theorem. What kind of problem am I doing? Proportion. Does central limit theorem apply to proportions? And a lot of people across all my classes are having issues with that this year. It's just one of the little things that they're forgetting. B, the confidence interval is valid because each resident was asked the same question. Well, should they have asked them all the same question?
Yes.
Does that make it valid? No. So they're just kind of trying to throw you off with that one. The confidence interval is valid because no conditions are required for constructing a large sample confidence interval. Is that true?
No.
Confidence interval is not valid because the quantity n times p hat is too small. The confidence interval is not valid because no opinion was included as a response category for the question. This is where wording is trying to throw you off here. If I am dealing with proportions, I am concerned with, so when I check normal for proportions, how do I check normal for proportions? So I'm doing something with n times p hat, and I'm also dealing with something with n times what?
The inverse.
In words, in general, what does this mean? Successes, what does this mean? So why is that confusing?
Because there's 3 options.
There's 3 options, and this is the wording part that's confusing. There was one constructed to estimate the proportion of residents who support the building waste management facility. So just like when I roll a die, there are 6 options, but I can condense it to be success and failure. So what are they considering success in this situation?
Yeah.
Which means what are they considering failure? And that's where people are going to get confused. So my n times p hat would end up giving me what here? Just 4. So n times p hat is not greater than or equal to 10. And E is, I talked through the problem basically talking about E. Yes, there were 3 options, but we can condense it to success or not success. Number 14. You'll probably see maybe 1 or so types of problems like this where it takes a lot of time to do this one multiple choice problem. Every single answer choice option makes you go do separate math to check it. Now, in going over it, it's a great problem to go over because we can go over 5 different types of things with one problem in the time span of just completing 40 multiple choice. It takes a lot of time to do it. All right, so of the 3 attitude groups, the group with the negative attitude has the highest proportion of type A personality types. So the group with negative attitude has the highest proportion of type A. So I'm just dealing with this one. What is the proportion? So I'm going to write negative proportion of A is what? How do I figure that one out? Like whatever what? We might be done in 15 minutes. No, I think we're ready. 24 over 43, which gives me what? Well, more than half. I can look at that and say more than half, right? Mm-hmm. But it's saying negative is the highest of type A. So neutral proportion of type A is what?
11.
Well, that's over half. This one's going to be more than that. And then this one, oh, these are all more than half. It's easier for me to deal with these in percents. I don't care if I tell you what they are, as long as you're following me how to get them. This one's like 55.8%. This one's 55%. This one is 67.6%. So is negative of the 3 has the highest of type A?
No.
No. What kind of probability is that called? Where I only dealt with like one specific and then found probability of something within that one specific? Conditional probability. So it wanted, most of these are dealing with conditional probabilities, you just have to do them correctly. Of the 3 attitude groups, the group with a neutral attitude has the highest proportion of type B. Why should this part be really easy to figure out what the answers are?
Because it's just the lowest of that one.
The opposite of these. So we've got 45%, 44.2, 33.4. So would neutral be the highest of type B? Yes, because it's going to be 45%. I don't know that I'm going to sit here and waste time to go through every single one of these. C, for each personality type, more than half of the 100 respondents has a neutral attitude. Can you look at that one and tell me it's right or wrong? For each personality type, each one of them has more than 50. Well, if I have more than 50, then we're not right in the first place. So that one isn't even really a correct one to do at all. I can keep going. These are 2 different. This one says and. Let's just look at E. More than half of the 100 respondents have type A and positive. Type A, positive. Is that more than half? No. So I would have done another conditional for part D to check it, but it ends up being false. All right, 23, and this is our 15th one. Julie generates a sample of 20 random integers between 0 and 9 inclusive. Means I can't have 0, I can't have 9. She records the number of 6s in the sample. She repeats this process 99 more times, recording the number of 6s in each sample. So each time she selects a number, what is the probability that it is a 6? 0.1, because 0 to 9, that's 10 numbers. How many of them are 6? 1. So the probability of getting a success is 0.1. How many is she doing? 20. So this goes back to you guys thinking of it like this. We flipped a coin 20 times. Each dot represented 20 coin flips, but our probability of success in that situation was 0.5. We just happened to put how many dots up there, how many dots would end up being up there. 100. So we'd have 100 dots, but each dot represents a sample of 20 and a probability of 0.1. So our N is what? Our N is 20, our P is 0.1, so our only possible option is C. How is it binomial switches it to success and failure, or success is 6 or failure is not 6. I think it's more important that, like, technically you could do a sampling distribution of something with this. So it really comes down to either one of these could work if they were done correctly. So it just happens to be the only one of those that work, and I think they kind of just try to break off of that part. When forming a test of significance about a population mean, a t-distribution instead of a normal distribution is often utilized. Which of the following is most appropriate explanation for this? I think a lot of you just did not read this problem correctly. Why do I use a t instead of a z? Everybody in here should know this one because I make you write it every single time you literally write z or t.
You don't have a sin.
Since sigma isn't no, or since we know, or since we only have s. So sample size is not large enough. That could possibly be in there with not being central limit theorem maybe. Sample does not follow normal distribution. That doesn't really make much sense right now. There's an increase in the variability of the test statistic due to the estimation of the population. Some of you are going to go through this really quick and pick this one, which I think was the most missed problem. Is this one correct? What is wrong in this? What's one word is wrong? And some of y'all are going through this one too quick and think, okay, we have to use the sample standard deviation because the population one is unknown, and y'all accidentally picked that one without thinking about it. So now, stepping out of that one, at this point, what happens when I switch from, when I have to use a sample instead of or statistic instead of a parameter? That means there's going to be a little bit of what? There's going to be some type of error in the problem, right? So which one of those would talk about the fact that there's going to be a little error because we had to estimate the parameter? We have to account for the error, which means there's going to be an increase in the variability because we had to account for that error, which is why the t statistic becomes closer and closer to the z as it gets bigger. That error is smaller the bigger our sample size is. For problem 28, a group of students has 60 houseflies in a large container and needs to assign 20 to each of the 3 groups. The groups are A, B, and C, the different treatments.
So we need to figure out which is the best way to assign these 60 houseflies into groups A, B, and C. So the first one says, label the first 20 flies caught. Well, this one says they capture the flies one at a time when it enters a side chamber in the container that is baited with food. So the first 20 flies that are caught are maybe the best at getting to the food, better somehow because they got to the food. Typically in problems like this, it's usually like the first 20 you caught would be like the slower ones, or but regardless, there is something in common of those 20 that are caught, which means there will be bias in the different groups. The different groups will not be the same. So B says write letters, so that's not good. We don't want bias. Write letters A, B, and C on separate slips of paper. Okay, we're starting better because we're at least dealing with some randomization there. Randomly pick one of the slips of paper and assign the first 20 caught to that group. Well, we didn't fix the bias issue. All we figured out is here I knew A was going to be the first 20. Here, the first 20 are still similar. Now I just don't know which group they're going to be in, but that doesn't account for my bias in the group itself. C says when each fly is caught, roll a die. If the die shows an even number, the fly is labeled A. If the die shows an odd number, it's labeled B. So we've got some randomization in which one goes to A and which one goes to B. When 20 flies have been labeled A and 20 have been labeled B, then the remaining ones are labeled C. So these still have something in common. So here we did better than A and B, but still C isn't really any better than it was before. The last 20 caught are still going to end up being in C. So even though it's getting better than A and B, it's still not there yet. Skipping down to E, when each fly is caught, roll a die. If the die shows a 1 or 2, it's labeled A. 3 or 4, it's labeled B. 5 or 6, it's labeled C. So we have taken ourselves out of the process of grouping, of how we group. We've also taken ourselves out of the process of assigning a treatment to that group. So equal chance of all of them. My issue here is what happens if, and I'll go extreme at first, what happens if every single roll of the die was a 1 or a 2? Then every single one of them would be A. And it doesn't have to be that extreme. It's just if there's any scenario other than the fact that there are exactly 21 or 2s, exactly 23 or 4s, and exactly 25 or 6s, then the groups wouldn't be the way they should be. So this does not ensure exactly 20 in each group, or doesn't actually ensure we get all of each group. They could have done something like they started to do in C, or they could say this was the case, but then once one of the groups has 20, then no more can go to that group, and then you can continue rolling and to put them in the other two groups. And if it happens to be a number that was from the group that's closed, you just roll again. So we were starting out better here, but it didn't finish right. B ends up being pretty much like the ideal scenario for how to do the random assignment process here. Place each fly in its own numbered container, and we're going to order it based off of the order that they're caught. We only use the order that they're caught just to give them the number. We then take those numbers, put them on equal size slips of paper, put them in a jar, mix them up, pick them one at a time. Pick 20 numbers out of the jar, assign the flies to that in the containers with those numbers to group A. The next 20 are group B. The last 20 are group C. This is pretty much your perfect example, or not perfect. This is definitely your best, very close to what exactly you need as your example for random assignment. This one I'm actually going to talk off topic a little bit about again. Consider a data set of positive values, at least 2 of which are not equal.
which of the following sample statistics will be changed when each value in the data set is multiplied by a constant whose absolute value is greater than 1? So let's break down the wording part a little bit first. What is it telling us to do to the distribution? One word. Multiply. If I am describing a distribution and I say the mean, that's the what of the distribution. More generic. Center. What kind of measure is this? What kind of measure is this? So these two are dealing with center. This one is dealing with spread. When we are dealing with stuff like that, it breaks down into categories like this. So center gets affected the same way, spread gets affected the same way. This is transforming data. And people get confused sometimes about which one's transforming and which one's combining. So transforming is one data set and do something to every number. Now I'm going to use super easy numbers here to deal with. Let's say we measure everybody's height in the class, and we end up getting our average to be 5 feet. So I'm dealing with easy numbers. Then I want to go back and change everything to inches. What is our new mean? 60 inches. All right, so our first thing there is multiply, which is the same thing as divide, and dealing with center. And then we're going to talk about add and subtract. The one thing about, and I know I'm writing it as center, but I always talk about it usually with mean. Across the entire class, pretty much, mean, what happens to mean is exactly what you would expect to happen to mean. So if I multiply or divide, what would you expect to happen to the mean? Multiply or divide. So we multiplied all of our individual values by 12 to change those to inches. Our center also multiplied, divided by inches. Or by 12 to get inches. Go back, we measured everybody, we were 5 feet tall on average. We went back, the scale was wrong. It was 2 inches short on every single person. We can go back and adjust all of them. What is our new average? Sorry, everybody should have been 2 inches taller. What's our new average?
5'2".
5'2". So what do we do? Exactly what we would think it would do. We add or subtract to it. So mean always is affected the exact same way you would expect it to. All right, so I've got a distribution. If I multiply it, it's like me stretching it. Didn't get much bigger. What happened to my spread when I multiplied? It multiplied. So that transformation happens how you would expect it to. If I added or subtracted, that's taking this distribution and just sliding it that way. What happened to my spread? When I multiplied or divided, what happened to my shape? From here to here, what was my shape here? Fairly what? What happened to my shape when I multiplied it? So the shape itself is still going to be the same. And what happens if I just take the distribution and slide it? Shape stays the same. So now we're going back to use this to answer our question. We multiplied or divided. So we are in this column right here. Does our mean change? Does our median change? Does our standard deviation change?
Yes.
And just because I wanted to write these two charts at the same time, I'm gonna go ahead and talk about combining, even though it's not part of this problem. So that was transforming data, which means we took one data set and did something to all of them. When we are combining two independent random variables. So like distribution A and distribution B.
Must be center of the meeting.
I am doing this one specific because usually when we do this is the way we deal with it, even though technically what you're asking, the way associating is. I'm just doing these specific. Alright, so I'm taking an entire distribution A, an entire distribution B, and putting them together. So this is my day job, this is my night job, I wanna see how much I made together. Mean, again, works exactly how you'd expect it to. This would be mean of A what? Plus mean of B. What about when I subtract them? It's exactly the way you would expect it to. And I know we talked about this one the other day, but I wanted to write it as charts while we were doing the other one. I know I'm going to start with standard deviation A, and I'm going to start with standard deviation B. What am I going to do mathematically right here?
State of variance.
Add on and put in state of variance, which means at the end I have to take it out of the state of variance. So what about here?
The same thing.
The exact same things. Our two rules are state of variance and always add, even if we're subtracting our two distributions. So like I said, I know I wrote this in a different way the other day, but some people like seeing these two charts together. And so that chart didn't have to do with this problem in particular, but I want to discuss them together. All right, number 11. I'm going to start this one at a point where I would not expect most of you to start, but it kind of gives you a hint for ways to address some of the problems on the AP exam. If I get a problem like this, I'm going to look at it really quick before I ever read the problem. I obviously have to pick which one's right, but the easiest way to start is what's different. So like, what is something that is changing in those graphs?
Q1, Q4 for real? Or Q2?
Definitely Q2, which is our median. Let's look at what's not changing. So what is the exact same for all of them? The outlier dot, the minimum, and the Q1. So we only now have, so if you can look at it real quick and see that, I can go, okay, I need to focus on the median, maybe the Q3, and where this line should be. Just looking at this that it gives us. So it says, hey, if I do this math, this is my math to figure out if it's an outlier or not. This is definitely something the question's asking about. Is this where my line goes to? So this is my cutoff as an outlier, as this where my line should go to. Okay, give me a wording of where your line should always go to. The last one that's actually in the data set that's not that far. Well, the cutoff would be here, so the last one that's not that far would be somewhere between what and what? 60 and 70? Well, not between 60 and 70, not between 60 and 70. Yes, yes. E is no, right? If I shifted, I'm good.
Yeah.
Okay, so we're down to C and D before I even really start this problem. But I'm still gonna talk about the whole problem even if you didn't do it that way. Alright, so I've got 26. Let's go over 5-number summary. What's the first thing in 5-number summary? Minimum, then Q1, median, Q3, and max. Well, I know where my min and max are. Those are all the same. So let's start with Q. Which one do I do first? Which one of the three things do I find first? Q1, median, or Q3? Median usually. So I've got 26. So I'm going to split it in half. So how many are in each half? Alright, so between my 13th and 14th number would be my median. So I'm 6, 10, 16. So my median is somewhere in that bar. If I've got 13 here, then my Q1 is my what number? My what number? What's the, so it's the 7th because it'd be 6 and 6. Or I could do n plus 1, 14 divided by 2, 7. So my 7th number is my Q1. So 6, past that. So my Q1 is somewhere in this bar. Where would my Q3 be?
Somewhere in between Q2 and Q3.
So here it was the 7th number. Here it's going to be the what? The 20th number. 13 plus 7. So my 20th number, or I could go backwards 7. 1, 2, 3, 4, 5. Somewhere in this bar. And these three things right here will get you exactly to your answer. I'm going to have to clear everything and then shift it. So my Q1 had to be between what and what?
10 and 20.
10 and 20. Well, we already said all the Q1s are the same. My Q2 had to be between what and what?
20 and 30.
So that one's not. 20 and 30, 20 and 30. That one's not. My Q4, which we had already narrowed down between here and here, but my Q3 has to be between
40 and 50.
40 and 50, 40 and 50. Nope. Yes. Yes. We've already checked where this one had to be and narrowed it down to between C and E, or C and D, so D ends up being our answer. And either direction you chose to start there, you're going to end up with the same answer. All right, number 40. Oh, I wanted to go back to one out of curiosity. I think I deleted the problem now. This problem said, consider a set of positive values, at least 2 of which are not equal. Why did it say that?
So you know that there's a range.
What happens if every single one of them were 0 or were the same number? There's no range and what?
The mean and the median are same.
Which means which of these three would be?
0.
So what happens if I multiply 0 by something? And that's why they had to say that. Which kind of comes down to that too, making sure that I'm saying that it gets bigger directly, because of those two things together. I just kind of wanted y'all to see if y'all understood that part of it. Okay, so this one says, which is our best one here? We are dealing with two different things. It tells us that the true value of the parameter is 0. So if that's our parameter, what do we want to do in relation to that parameter? So we want, visually, we want our what to be where? Center to be at 0. This one, the center, that looks definitely at 0. This one, the center, maybe not perfect, but that center looks decent. Might read okay. Here, I'd probably say that that center does not look good, but I'm not real sure. Here, center is definitely not at 0. Here, the center is definitely not at 0. So I've looked at the center for each one. What's the other thing I want to account for if I'm trying to do a better one?
Spread.
And what kind of spread do I want to be what I call quote unquote better?
No, closer spread.
A smaller spread. So is this a good spread? That one's too spread out. Is this a good spread?
Yep.
Not a good spread. Here the spread is good, but the center was bad. Here the spread is good, but the center was bad. So now, which is our best choice? It might not be perfect, but of our answer choices, it is definitely the best one. Yep. I probably wrote 2 spread. For which one are you talking about? Yeah, I was just writing those. I should have wrote high spread. High spread didn't make one. All right, 24. All right, so we are comparing 2 different box plots. Without even reading context there, the interquartile ranges are the same for both samples, yes or no? No. Interquartile range, those are definitely not the same. Range for species B is greater than the range for species A, yes or no? Because the ranges are what? Because range, those are the same for both of them. There are more petal lengths. So if I'm comparing one to the next of a box plot, is it always okay to just say there are more in one than the other? What is a better word choice here? What is a better way to say that when I'm comparing 2 box plots that I know absolutely nothing about? What do I know about this box right there? So if I just say, tell me about that box, tell me something very descriptive in numbers you can tell me about that box. So what's a better way than saying straight out more? And I want you to, this is outside of this problem, but I want you to understand why this is an issue a lot of the times. So why in this problem am I okay saying more? And keep in mind, I skipped all this on purpose so we can come back to it. So why am I okay in this particular problem saying more instead of higher percent? Based off of wording up here.
Because it's number of petals. Or it's like.
It tells me something. If it hadn't told me that, I would have to say only higher percent and not more. That is not throwing you off on this problem at all, but it is a really good thing to make sure you understand. So like if you're doing a free response and you keep saying there are more of one than the other, they are going to count off if you don't know the sample sizes, and specifically if you don't know the sample sizes are the exact same. Because I could have 100,000 in this group and 10 in this group. I can't say there are more between here and here than there. I can just say higher percent. So now, off of that side note, now that I know I can directly compare these because of the two equal sample size, let's talk about it like percent because it makes more sense. What percent do I know in species A that are greater than 70 millimeters?
Less, like a little less than 25%.
A little more than 25%, because this is 25%, so a little more, oh wait, A, yes. Look at the other one, right? I have that switched right now, right? So it should be, so 70 is here, this is 25%, so I just know that it's less than 25%. B, instead, is gonna be what? More than 25%. Is this one more than this one?
No.
So now I'm gonna go here to, it's saying greater than 40. So in species B, what percent is greater than 40? What percent of A is greater than 40? Is this one greater than this one? Is less than 50% greater than more than 50%? And then my last one, I'm talking about less than 30. So in species B, what percent is less than 30? More than 50%. In species A, it's about what? About 25%. There are more that are this than that. Is that one correct?
Yeah.
Your answer is E there. I think that's one of the ones where if people aren't literally writing stuff out like this and thinking through it, you can easily try to do it in your head and write it down wrong. Number 39. I have seen this problem, or a very, very similar problem to this problem, multiple times. And I think the way they word this problem gives you too much direction. I've seen it written to where it's the exact same problem, but they take out a part of it without giving you as much of a hint, and I like that kind of problem better, to be honest. The weights of population of adult male gray whales. So I've got the approximately normal, here's my mean, here's my standard deviation. So gray, got approximately normal with a mu of 18,000 and a standard deviation of 4,000. And then it talks about humpback whales. It gives me my approximately normal again. Now I have a mean of 30,000 and the standard deviation of 6,000. A certain adult male gray whale, so I'm back in this column again, has a weight of 24,000. So this one value is 24,000. This is where the problem gives me more than I've seen it before. It would be fine if it said a gray male of 24,000 would be the percent of gray males that were under this amount would be under the same amount for what in a humpback male, and not explicitly tell you that. I think that's giving you too much information. So I can switch this one to a z-score. Plug in my numbers, tell me what to write first.
24,000 minus 18,000 divided by 4,000.
Well, 24 minus 18 gives me 6,000. 6 over 4 gives me 1.5. So now it's saying, where would a z of 1.5 be if I now jumped over and went to this distribution? So now I'm starting with my z equals 1.5 and solving for x with a mean of 30,000 and a standard deviation of 6,000. So 6,000 times 1.5 gives me what? What's half of 6,000?
9,000.
3, so it gives me 9,000, so it gives me 39,000. And like I said, I think if you saw that problem, it would not be obvious enough to tell you in between that you should do a z-score. Yes.
The previous column, you don't wanna if there's just a larger space.
Are you talking about this one?
If there's a larger space, doesn't mean there's a higher percentage, which is spread out minus marks.
Correct. So like basically I can't say any details at all about anything between here and here. The only thing I can say is I know that this is 25, so I know that this is less than 25 and this is more than 25, but I can't say anything about like the difference between. If they ask me something about this number versus this number, I have no information to get me any more detail in between the gaps. Yes. To answer your question shortly, yes. Number 6. I'm going to answer this question by not answering the question at all. I'm going to talk about the answer choices. We're talking about a coin flip, and there are 5 of them. So let's kind of use that to talk through these. C, what kind of a probability is C? What's the only thing we have that starts with something like this that isn't a fraction? It starts with a number over a number.
Binomial.
So this is a binomial. While we're at it, everybody on your orange sheet, find where it talks about binomial. Just so that we're starting to get used to where things are on the orange. And remember, if we do binomial, we usually use our calculator, but we still need to know this equation. So what's the number that goes there? So our n is 5. Well, that looks good. What number goes here? Which is what? My number of xk, yes, both of those are correct. In context, that's my number of successes. I usually call it x, I know the equation she calls it k. And then the other thing it uses is what? Binomial have an N, an X, and a, what's my P in this problem?
One, two.
Now, in this one, the only thing that's different about what they have as this answer choice and your equation for binomial is if I have one success, what number should this be? So they actually wrote it to where they switched these two. But this is a binomial with an N of 5, one success, probability of 1/2. They just switched those two numbers. This is saying I got 1/2 4 times, and then I got 1/2. What kind of probability do you think that is? Think about back to when we used to deal with this one. And so geometric, what's the difference between binomial and geometric? In binomial, we count the successes out of total. What does geometric do?
Successes compared to failures, right?
To an extent, but how many successes do I get? Like,
One.
you get one, you're doing it until. So this is success, and this is failure. Now, I would need more context there, but trying to relate it back to the problem, this would be like maybe, since it's talking about heads, getting tails 4 times in a row, and then my 5th one being heads. Now, obviously, I could write it different ways to get that exact same thing, but just trying to make association there. If a probability is 0, what does that mean? Never happens. If a probability is 1, what does that mean?
Always happens.
Alright, so now let's actually go back to the problem. A coin is to be flipped 5 times. First 4 flips land heads up. What is probability of heads on the 5th flip of this coin? Does it ask us to find the probability that the first 4 were heads and the 5th being heads?
No.
It said all of this has already happened, so it's only asking what that 5th one is. I don't care what the first 4 was because coin flips are what? And it does not ask what scenario that all of this happened. It's saying, okay, yeah, I'm gonna give you some background knowledge, it doesn't matter. Now, what's the probability that my next one is this? You have about 40?
Yes.
Okay.